Video models are excellent at generating realistic motion, but they frequently fail at multi-step logical reasoning. When a model generates a video of a maze or a puzzle, it must plan ahead. Traditional models either guess frame by frame and make irreversible mistakes, or try to plan everything at once, which is incredibly slow. Today, we are exploring hierarchical denoising for visual reasoning, or HDR. This framework organizes video generation into a tree-structured hierarchy, allowing models to plan globally while streaming frames efficiently. Existing video generation paradigms force a trade-off between reasoning quality and streaming speed. Autoregressive models generate left to right. They are fast, but if they make an early mistake, they cannot backtrack, leading to logical failures. Bidirectional diffusion models can revise their plans globally, but they must denoise the entire sequence of dense frames at every single step. This makes them far too slow for real-time streaming. HDR resolves this tension by introducing a hierarchical structure that separates high-level planning from low-level frame generation. HDR represents videos as a tree-structured hierarchy of latent tokens to enable coarse-to-fine reasoning. As shown in the architecture diagram, HDR organizes video latents into multiple temporal resolutions. The top, coarse layers represent high-level plans and global structure. The bottom, fine layers encode local visual details. During inference, the model generates tokens from coarse to fine. This allows the model to establish a solid global plan in the upper layers before committing to the exact visual details in the lower layers. A key design of HDR is its entropy-matched denoising schedule, which preserves planning uncertainty in coarse layers. Instead of fully denoising every layer, HDR matches the denoising strength to the hierarchy level. Coarse layers are intentionally stopped at higher noise levels. This allows them to remain partially stochastic, preserving multiple possible global plans. Finer layers receive stronger denoising to resolve these plans into concrete visual states. This prevents the model from prematurely collapsing its hypotheses. To keep computation fast, HDR introduces the Sparse Hierarchical Attention Pattern, or SHAP. In standard models, every token attends to every other token, which is computationally expensive. SHAP restricts each token's attention to its local neighbors, its parent token in the coarser level, and the first frame. This sparse structure enables multi-scale information flow through a shared KV cache, while keeping the computational complexity linear with respect to video length. HDR achieves massive gains in reasoning accuracy while maintaining low latency streaming. In multi-step reasoning benchmarks like the Tower of Hanoi and maze navigation, HDR improves overall success from 34.22% to 60.29% compared to streaming baselines. Remarkably, it maintains a low latency of just 0.70 seconds per latent, which is over 54 times faster than bidirectional diffusion. It also shows incredible data efficiency, retaining over 80% of its success rate with only 2% of the training data. Beyond synthetic benchmarks, HDR's hierarchical reasoning successfully transfers to physical-world robot manipulation. Researchers tested HDR on a real-world robot arm navigating physical mazes. By combining HDR with an inverse dynamics model, the robot could plan and execute actions in real time. HDR maintained high success rates across easy, medium, and out-of-distribution physical layouts, demonstrating its potential as a robust world model for physical interaction. Despite its success, HDR can still suffer from late-stage state consistency drift. Because the model's errors are rarely complete planning failures, they usually manifest as minor physical inconsistencies near the end of a video. For example, a wall might suddenly disappear in a maze, or liquid colors might blend incorrectly in a water-pouring task. Future work will focus on integrating constraint-aware refinement or lightweight verification steps to ensure absolute physical consistency in the final frames.